Welcome to our deep dive into quantum accelerometers. We'll be taking a close look at this amazing technology based on an essay by Jürgen Schneppat.
It's called Quantenbeschleunigungsmesser. Precision durch Quantenphysik.
Wow, that's a mouthful.
It is. But the technology itself is even more impressive. We're talking about sensors that could revolutionize how we navigate, understand our planet, and even diagnose diseases.
That's a bold claim. What makes these quantum accelerometers so different from the sensors we use today?
Well, they operate on completely different principles, using the strangeness of quantum mechanics to achieve incredible levels of precision and stability.
Quantum mechanics. Sounds complicated.
It can be. But the basic idea is that quantum accelerometers harness the wave-like nature of atoms to measure acceleration. It's mind-blowing stuff, really.
Okay, I'm intrigued. So let's start with the basics. What exactly is a quantum accelerometer?
At its core, it's a device that measures acceleration.
Okay, sure. But how is it different from the accelerometer in my phone, for example?
Instead of relying on mechanical parts or electrical signals, quantum accelerometers use atoms.
Atoms? How can you use atoms to measure acceleration?
It involves a technique called atom interferometry. You see, atoms can behave like waves. We use lasers to manipulate these atomic waves, splitting them and recombining them.
And by analyzing how these atomic waves interfere with each other, you can determine the acceleration.
Precisely. Any acceleration the atom experiences will affect its wave-like behavior, causing a shift in its phase, which we can then measure.
That's incredible. Schneppat actually gives a formula for this phase shift in his essay, right? Something like H1, H2, AO, H1, H2.
That's the one. It looks complicated, but it basically describes how the energy difference between the atom's split paths, which is affected by acceleration, translates into a measurable phase shift.
Still a bit over my head. Can you break it down a little more? What are those H1 and H2 things?
Those are called Hamiltonian operators. Don't worry too much about the name. Basically, they represent the total energy of the atom along each of its possible paths. Okay, so it's like comparing the energy fingerprints of the atom along different routes to figure out how much it accelerated.
Exactly. Pretty ingenious, right?
Definitely. But why go through all this trouble with lasers and atoms? What makes quantum accelerometers so much better than the ones we have now?
There are three main advantages: precision, stability, and their ability to work in extreme environments.
Okay, let's break those down. What do you mean by precision?
Well, quantum accelerometers are based on atomic standards, which are fundamentally more precise than any man-made measurement tool. It's like having a ruler that's perfectly calibrated down to the atomic level.
That's amazing. So they're more accurate because they rely on the unchanging properties of atoms.
Precisely. And that brings us to stability. Unlike classical accelerometers, which can be affected by temperature changes, aging, or wear and tear, quantum accelerometers are virtually immune to those things.
Wow, so they're incredibly reliable too. No more worrying about your phone's accelerometer going haywire because it got a little too warm. Exactly. Imagine the implications for self-driving cars, drones, or even spacecraft exploring distant planets. They need sensors that are both precise and incredibly reliable.
I'm starting to see the appeal. So if these quantum accelerometers are so great, how do we actually build one? What are the key ingredients?
The heart of it all is the atom interferometer, which uses a source of ultra-cold atoms, often alkali metals like rubidium or cesium.
Ultra-cold. How cold are we talking?
Near absolute zero, which is mind-bogglingly cold, as you can imagine. It's essential for manipulating them with those laser pulses we talked about.
Wow, sounds like a challenge to keep things that cold.
Yeah.
So we have these super cool atoms. What's next?
Then we use carefully calibrated laser pulses, which act like beam splitters, mirrors, and recombiners for the atoms, creating a sort of obstacle course that guides them along specific paths.
And those paths are where the atoms experience different accelerations, causing the phase shift that you can measure, right?
You got it. And to detect those tiny variations, you need a super sensitive detection system.
So it's a pretty complex setup then. No wonder we don't see quantum accelerometers in our phones just yet.
Miniaturization is definitely one of the big challenges. It's not easy fitting all those lasers, cooling systems, and detectors into a small package.
I can imagine. It sounds like trying to fit a whole physics lab into something the size of a smartphone.
It's not that far off. But despite the challenges, the potential rewards are immense. A portable quantum accelerometer would revolutionize so many fields.
I'm sold on the potential. So what are some of the most exciting applications for these devices, both now and in the future?
One of the biggest ones is navigation without GPS.
Like using them in submarines or spacecraft where GPS signals can't reach?
Exactly. Quantum accelerometers could enable incredibly precise inertial navigation, allowing vehicles to track their movements without relying on any external signals.
So we're talking about creating a self-contained navigation system that operates solely on the laws of physics.
Precisely. And the precision we're talking about is astounding. We could pinpoint locations with centimeter-level accuracy, even after hours of travel.
That's incredible. That opens up so many possibilities, not just for vehicles, but also for wearable devices, augmented reality, even navigating inside buildings where GPS doesn't work well.
Absolutely. And that's just one application. Quantum accelerometers also hold enormous potential for things like geophysics and Earth observation.
Oh, right. I remember Schnepp mentioning something about using them to study earthquakes and tectonic activity.
That's right. By detecting tiny variations in Earth's gravitational field, we could map underground structures, locate resources, and maybe even predict earthquakes more accurately.
So we're talking about creating a kind of gravitational map of the Earth's interior, revealing all sorts of hidden secrets.
Exactly. It's like having X-ray vision for our planet. Pretty cool, huh?
Definitely. It seems like quantum accelerometers are not only revolutionizing our understanding of the Earth, but also opening up new frontiers in space exploration.
Absolutely. But we've only scratched the surface of what these devices can do. We'll delve into even more mind-blowing applications in our next deep dive.
Last time we talked about the amazing potential of these quantum accelerometers, but I have to admit I'm still a little fuzzy on how this whole atom interferometry thing actually works.
It's definitely a bit mind-bending, but once you grasp the basic concept, it's actually pretty elegant.
Okay, well, I'm all ears. Walk me through it. How do you actually use atoms to measure acceleration?
All right, so picture this. We start with a cloud of ultra-cold atoms cooled down to almost absolute zero, trapped in a special chamber.
Absolute zero, like the coldest anything can possibly be.
You got it. And this extreme cold is what allows us to control these atoms with such precision. Okay, so we have our super-cooled atoms. The next step is to hit them with a very specific type of laser pulse. It's called a Raman pulse.
Raman pulse.
Mm-hmm.
Well, that sounds familiar. Didn't we talk about Raman spectroscopy in a previous deep dive?
Sharp memory. Yes, Raman spectroscopy uses a similar principle, but instead of analyzing molecular vibrations, we're using these Raman pulses to very precisely control the energy states of our atoms.
Gotcha. So we're using lasers to nudge these atoms into specific energy levels, but how does that help us measure acceleration?
Okay, this is where the wave-like nature of atoms comes into play. That first Raman pulse acts like a beam splitter, putting the atom into a superposition of two states.
Superposition, you mean like the atom is in two places at once?
Exactly. It's one of those mind-boggling aspects of quantum mechanics. The atom is essentially existing in two different energy levels and traveling along two distinct paths simultaneously.
Wow, okay. I'm trying to wrap my head around that. So the atom is on two paths at the same time. What happens then?
Because those two paths are slightly different, the atoms on each path will experience slightly different accelerations.
Makes sense. So how do we measure that difference?
Well, that difference in acceleration causes a phase shift between those two parts of the atom's wave function. It's like two waves that start out in sync but then gradually drift out of phase because they're experiencing slightly different conditions.
I'm with you so far. Then what?
We then hit the atoms with a second Raman pulse. This one acts like a mirror, reflecting those atomic waves back towards each other.
Okay, so we split the atom's wave, send it along two paths, and now we're bringing them back together. What happens when these two waves, now out of sync, meet up again?
They interfere with each other, and this interference creates a very specific pattern, bright and dark fringes that we can measure with our detectors. This pattern directly reflects the phase shift, which was caused by that acceleration the atoms experienced.
So it's like each path the atom took tells a story about the forces it encountered, and this interference pattern allows us to read that story.
You got it. And the level of sensitivity is just incredible. We're talking about measuring accelerations that are billions of times weaker than the force of gravity.
Wow, that's mind-boggling. So like we've created a microscope for motion.
Exactly. And because these measurements are based on fundamental atomic properties, they're incredibly stable. Unlike those classical accelerometers, they're not affected by things like temperature changes or wear and tear.
So to recap, we have this incredibly precise and stable system for measuring acceleration using lasers and atoms. But Schnepp also mentions magnetic fields playing a role in all of this. What's their part in all this?
Magnetic fields are crucial for fine-tuning the atom interferometer. They help us control the energy levels of the atoms with even greater precision. And just as importantly, they shield the atoms from unwanted external influences.
What kind of unwanted influences?
Well, any stray magnetic fields, even the Earth's own magnetic field, can interfere with those delicate measurements. So we use carefully calibrated magnetic fields to basically create a protective shield around our atoms.
But we're building this, isolated world for our atoms where we can perfectly control everything.
You could say that. It ensures that we're measuring only the accelerations we're interested in. It's this level of control that allows quantum accelerometers to achieve those incredible levels of sensitivity and stability.
This is all very impressive, but it does sound like a pretty delicate setup. No wonder we're not seeing pocket-sized quantum accelerometers just yet.
Yeah, miniaturization is a big challenge. Right now, researchers are doing some really exciting work on things like chip-based atom traps, trying to shrink all those lasers and magnetic coils down to the size of a microchip.
A quantum accelerometer on a chip. That would be amazing.
Right. It would open up a whole new world of possibilities. Think about smartphones that could navigate with incredible accuracy, even without GPS.
Or imagine medical sensors that could detect tiny tremors, maybe even diagnose neurological conditions in their earliest stages.
Exactly. But shrinking down the hardware is only part of the challenge. We also need to develop sophisticated software and algorithms to process the data from these quantum sensors.
Right, because all that data from the atomic world needs to be translated into something we can understand and use, right?
Exactly. And this is where things like artificial intelligence and machine learning come in. AI can be a powerful tool for analyzing the complex data streams from these quantum accelerometers, filtering out noise, and finding those subtle patterns that we might miss otherwise.
So it's like we're building a digital brain to help us make sense of all the data coming from the atomic world.
That's a great way to put it.
Yeah.
And it really highlights how interdisciplinary this field is. We need physicists, engineers, computer scientists, even medical experts all working together.
It's a true team effort, all driven by this desire to explore and innovate. But even with all this progress, I imagine there are still some pretty big hurdles to overcome.
Of course. We've talked about miniaturization and the need for better software, but there are other challenges too. One of the biggest is maintaining that incredible sensitivity over long periods. Even the tiniest environmental fluctuations can throw off our measurements.
So it's like we need to create even better shielding to protect those supersensitive atoms from any disturbances.
That's one approach. We're also looking at new materials and fabrication techniques that can make our quantum sensors more stable and resilient. And then there's the issue of calibration.
Calibration. Even though atoms are like the ultimate timekeepers, we still need to make sure our devices are staying accurate.
Absolutely. It's like with those incredibly accurate atomic clocks, we still need to check and adjust them to keep them precise. Developing reliable and efficient calibration methods is essential, especially if we want to use these quantum accelerometers in everyday applications.
Okay, so it sounds like there's still work to be done before we see quantum accelerometers in all our devices.
Definitely. But the progress being made is remarkable, and the potential payoff is huge. There's a lot of exciting research going on.
What are some of the most promising areas? What could really push this technology forward?
One of the most important areas is material science. We're always searching for new materials that can trap and cool atoms more efficiently. Plus, we need better ways to create those intricate chip-based structures. And of course, we need to develop even better lasers.
Better lasers.
Yeah, lasers that are more stable, more compact, and more energy efficient. That would be a huge step towards miniaturizing these devices.
It sounds like it's not just about the atoms themselves, but also about refining the tools we use to control them.
Exactly. And we can't forget about the software. We need to keep developing smarter algorithms that can filter out noise, find patterns, and make sense of all the data coming from those quantum sensors.
It's fascinating to think that we're combining all these different fields, physics, engineering, computer science, to unlock the potential of these devices.
That's what makes this field so exciting. We've covered a lot of ground today, from the inner workings of atom interferometry to the challenges and opportunities ahead. But before we wrap up, I'd love to dive into some of the more, shall we say, mind-blowing applications of quantum accelerometers.
Mind-blowing. I'm intrigued. Let's hear it. Last time we talked about some of the challenges researchers are facing, things like miniaturization and developing better software. But I'm really curious about those mind-blowing applications you mentioned.
Well, Get ready to have your mind blown because we're going to talk about using quantum accelerometers to see what's hidden deep beneath the Earth's surface.
Okay, you have my attention.
I remember we talked about those gravitational anomalies.
You have those tiny variations in Earth's gravity.
Right. Well, those variations are caused by differences in density underground. And by creating really detailed maps of those gravitational anomalies, we could pinpoint all sorts of things.
What sorts of things?
We could locate underground caverns, aquifers, mineral deposits, even archaeological sites.
Wow, all without digging a single hole.
Exactly. It's like having X-ray vision for our planet.
That would be incredible. Think of all the applications.
It would revolutionize resource exploration. We could find new sources of water, minerals, and energy in a way that's much less destructive to the environment.
That's a great point. It's not just about advancing our understanding of the world, but also about doing it sustainably.
Absolutely. And it's not just limited to Earth.
Oh.
Imagine sending a spacecraft equipped with a quantum accelerometer to Jupiter's moon, Europa.
Europa, the one with the possible subsurface ocean.
That's the one. By mapping its gravitational field, we could learn so much about its internal structure, like the depth and extent of that hidden ocean.
And maybe even find evidence of life.
It's a possibility, and that's just the beginning. We could even use quantum accelerometers to detect gravitational waves.
Gravitational waves, like those ripples in space-time.
You got it. They're caused by some of the most violent events in the universe. And right now, our detectors for those waves are huge and incredibly complex. But quantum accelerometers could offer a way to build much more compact and sensitive instruments.
So we could potentially detect gravitational waves from sources much farther away.
Exactly. It would be a whole new way of looking at the universe.
Amazing. So we've talked about exploring the Earth, other planets, and even the cosmos. What about closer to home? Any applications in healthcare?
Lots of potential there, too. Think about wearable sensors that can detect the slightest tremors in your movements.
That could be huge for diagnosing conditions like Parkinson's disease.
Right. Early diagnosis is key. Plus, we could use them for stroke rehabilitation, helping patients regain motor function more effectively.
It's like having a personalized physical therapist, monitoring your every move.
And there are applications for medical imaging, too. Quantum accelerometers could lead to new types of scanners that are much more sensitive and precise.
So we could detect things like cancer or heart disease at much earlier stages.
Exactly. And we could even use them to guide minimally invasive surgeries, helping surgeons operate with incredible accuracy.
That's incredible. It sounds like quantum accelerometers have the potential to revolutionize so many aspects of our lives.
They really do. But as with any powerful technology, there are important ethical considerations. We need to have serious discussions about privacy, security, and accessibility. We need to make sure these tools are used responsibly.
I agree. Well, we've covered a lot of ground in this deep dive into the world of quantum accelerometers. A huge thank you to Jorgo Schneppet for his fascinating essay, which sparked this whole conversation.
It's been a pleasure discussing this with you.
I am truly amazed by the potential of this technology. It makes me incredibly excited about the future and what we might discover. Until next time, keep exploring and never stop asking questions.